Welcome to our comprehensive tutorial on PyTorch LSTM networks. Today we're diving deep into long short-term memory networks, one of the most powerful architectures for sequence processing. We have 4 key learning objectives for this session. First, we'll understand the LSTM architecture and its internal components. Second, we'll master the torch.nn.LSTM API parameters and see how each one affects our model's behavior. Third, we'll build practical LSTM models for real-world sequence processing tasks. And finally, we'll explore advanced configurations like bidirectional and multi-layer setups. By the end of this tutorial, you'll have a solid foundation in using LSTMs effectively in PyTorch. Let's start by setting up our environment. We're importing PyTorch and its neural network module, along with NumPy for numerical operations, and Matplotlib with Seaborn for creating beautiful visualizations. I'm setting a nice visual style here and fixing the random seed to 42 to ensure our results are reproducible. This setup gives us everything we need to explore LSTM networks thoroughly. Perfect, our environment is ready. The random seed has been set, which means all our random operations will produce consistent results throughout this tutorial. Before we dive into code, let's understand what makes LSTM cells special. This diagram shows the internal architecture of an LSTM cell. The key innovation here is that LSTM cells maintain 2 types of state. They have the hidden state, denoted as H, which is what we typically think of as the output, and they also have the cell state, denoted as C, which acts as a long-term memory. This dual-state system allows LSTMs to capture long-term dependencies in sequences much more effectively than vanilla RNNs. The cell state flows through the network with minimal transformations, while various gates control what information to keep, forget, or output. Now let's move to our simplest example. We're creating a basic LSTM here with an input size of 10 features and a hidden size of 20. This means each input vector has 10 dimensions, and our LSTM will produce 20-dimensional hidden states. We're then creating some random input data with a sequence length of 5, batch size of 3, and our 10 input features. Notice the shape order here: sequence length comes first, then batch size, then input features. This is PyTorch's default format. When we run the forward pass, the LSTM returns 2 things: the output tensor containing all hidden states across time, and a tuple with the final hidden and cell states. Excellent, let's look at these shapes. Our input was 5 by 3 by 10, representing 5 time steps, 3 samples in our batch, and 10 input features. The output is 5 by 3 by 20, giving us the hidden state at each time step. The final hidden state H_n and cell state C_n both have shape 1 by 3 by 20. That first dimension of 1 represents we have a single layer LSTM. All our assertions passed, confirming the shapes match our expectations perfectly. Here's a comprehensive reference table for all LSTM parameters in PyTorch. This is really important to understand. We have required parameters like input size and hidden size that define the core dimensions. Then we have optional parameters that control the architecture. NumLayers lets you stack multiple LSTM layers. Batch first changes the tensor dimension ordering. Dropout adds regularization between layers, but note it only works when you have more than one layer. Bidirectional processes sequences in both directions, effectively doubling your output size. And projection size can reduce the dimensionality of the hidden state for efficiency. Each of these parameters significantly affects how your model processes sequences. This diagram illustrates how multi-layer LSTM networks are structured. When we stack multiple LSTM layers, each layer takes the output from the previous layer as its input. The information flows both horizontally through time and vertically through layers, creating a deep temporal processing network. This architecture allows the model to learn increasingly abstract representations of the sequence data at each layer. Let's implement a multi-layer LSTM with 3 layers. Notice how we're initializing the hidden and cell states for all layers. The shape of these initial states is NumLayers by batch size by hidden size. When we run the forward pass with these initialized states, the output still comes only from the final layer, maintaining the same shape as before. However, the returned hidden and cell states now contain the final states for all 3 layers, which is why their first dimension is 3. Perfect. Our multi-layer LSTM is working correctly. The output shape remains 5 by 3 by 20 because we only get the output from the topmost layer. But look at the hidden and cell states, they're now 3 by 3 by 20, containing the final states from all 3 layers. This is crucial to understand. In a multi-layer LSTM, each layer maintains its own hidden and cell states. Let's visualize the hidden states across our 3 layers. This utility function will create a heat map for each layer's final hidden state, helping us see how information is transformed as it flows through the network. Beautiful! We can see 3 distinct heat maps, one for each layer. Notice how the patterns differ across layers. Layer 1 shows the initial processing of the input, Layer 2 refines these representations, and Layer 3 produces the final abstract features. The color variations indicate different activation levels across hidden units and batch samples. This visualization really helps us understand how deep LSTM networks create hierarchical representations. Now let's explore the batch-first configuration, which is really important for practical applications. Here we're comparing 2 LSTM configurations, one with batch-first false, which is the default, and one with batch-first true. The key difference is in the input and output tensor shapes. With batch first false, we use sequence length, batch features ordering. With batch first true, it becomes batch sequence length features. This might seem like a small detail, but it's crucial for integration with other layers and frameworks. Notice that regardless of the batch first setting, the hidden and cell states always maintain the same shape, with num layers and batch dimensions first. Great, we can clearly see the difference. With batch first false, our input is 5 by 3 by 10 and output is 5 by 3 by 20. With batch first true, input becomes 3 by 5 by 10 and output is 3 by 5 by 20. The batch dimension has moved to the front, but notice the hidden state shape is identical in both cases, 1 by 3 by 20. This consistency in hidden state format is really helpful when working with multiple LSTM configurations. This diagram shows how bidirectional LSTMs work. In a bidirectional setup, we process the sequence in both forward and backward directions simultaneously. The forward LSTM reads from the beginning to the end, while the backward LSTM reads from the end to the beginning. This allows the network to have complete context at every time step, combining information from both past and future. Let's implement a bidirectional LSTM. When we set bidirectional equals true, the output size doubles because we're concatenating the forward and backward hidden states. The output shape becomes sequence length by batch by 2 times hidden size. We can reshape this output to separate the forward and backward components. The hidden state also changes. Its first dimension becomes 2, representing the 2 directions. Perfect! Our bidirectional LSTM output has shape 5 by 3 by 40, which is double the hidden size of 20. The hidden state is 2 by 3 by 20, with the first dimension representing forward and backward directions. We've successfully split the output into forward and backward components, each maintaining the original hidden size of 20. This bidirectional processing is incredibly powerful for tasks where context from both directions matters. Now let's visualize how the forward and backward LSTM outputs differ. This will help us understand what each direction captures from the sequence. Fascinating! Look at these 2 heat maps. The forward LSTM output on the left shows how information accumulates from the beginning of the sequence, with patterns that evolve from left to right across time steps. The backward LSTM output on the right shows the opposite pattern, with information flowing from the end of the sequence backward. The different color intensities and patterns demonstrate how each direction captures unique aspects of the sequence. When combined, these complementary views provide rich bidirectional context. Let's explore Dropout for regularization, which is essential for preventing overfitting in deep LSTM networks. Here we're creating an LSTM with 3 layers and 30% dropout between layers. This is important. Dropout only applies between layers, so you need at least 2 layers for it to have any effect. We're comparing the model's behavior in training versus evaluation mode. In training mode, Dropout randomly zeros some connections, causing variation in the output. In evaluation mode, Dropout is disabled, giving us consistent results. Let's run the same input multiple times and measure the standard deviation to verify Dropout is working. Excellent demonstration of dropout behavior. In training mode, we see a standard deviation of about 0.004, showing that dropout is creating variation in our outputs. In evaluation mode, the standard deviation is essentially 0, confirming that dropout is disabled and we get deterministic results. The sample outputs show how the values change slightly each time in training mode due to the random dropout. This regularization is crucial for training robust LSTM models. Now let's look at LSTM with projection, which is a more advanced feature for reducing model parameters. We're creating an LSTM with a hidden size of 64, but a projection size of 32. This means internally, the LSTM computes 64-dimensional states, but projects them down to 32 dimensions for the output. This projection happens for the output and hidden state, but not for the cell state. The cell state maintains its full 64 dimensions because it needs to preserve all the information for the internal LSTM computations. This technique significantly reduces parameters when stacking multiple layers. Perfect. Our projection is working as expected. The output shape is 5 by 3 by 32 using the projected dimension. The hidden state is also projected to 2 by 3 by 32, but look at the cell state, it maintains the full size at 2 by 3 by 64. This asymmetry is by design. The cell state needs its full capacity for the LSTM's internal memory, while the projected hidden state reduces computational cost for subsequent layers. Now let's put everything together in a practical example, building a sequence classifier that combines multiple LSTM features we've learned. Here's our complete LSTM classifier. We're using a 2-layer bidirectional LSTM with dropout for the encoder and batch first equals true for convenience. The LSTM processes the entire sequence, then we take the final time steps output for classification. Since it's bidirectional, we get features from both the forward and backward passes at that final position. These features are then passed through a fully connected layer to produce class logits. This architecture is commonly used for tasks like sentiment analysis or sequence classification. Excellent, our sequence classifier is working perfectly. It takes input sequences of shape 32 by 20 by 50, processes them through the bidirectional LSTM, and produces 10 class logits for each sequence. The model has over 582,000 parameters, which gives us plenty of capacity for learning complex patterns. This architecture forms the backbone of many practical NLP and time series applications. Let's simulate a training process to see how our LSTM classifier learns. We'll generate synthetic sequential data with class-specific patterns and train the model to recognize these patterns. Wonderful training dynamics. Look at these plots. The training loss on the left shows a nice decreasing trend, starting high and gradually converging as the model learns the patterns in our synthetic data. The accuracy plot on the right shows improvement from random guessing to much better performance. Our final loss of 0.85 and accuracy of 0.78 demonstrate that the LSTM successfully learned to classify sequences based on their temporal patterns. This visualization really helps us understand how LSTMs learn over time. Now let's dive deeper into the internals by examining the LSTM weight structure and initialization. Here we're examining the internal weight structure of an LSTM. Each LSTM layer has weights for 4 gates: the input gate, forget gate, cell gate, and output gate. That's why the weight matrix has 4 times hidden size rows. We can split these weights to see each gate's parameters separately. PyTorch initializes these weights uniformly in a range based on the hidden size, specifically from negative to positive 1 over square root of hidden size. This initialization helps maintain stable gradients during training. Perfect analysis of the weight structure. Each gate has its own 20 by 10 weight matrix. The initialization range is approximately negative 0.22 to positive 0.22, and we can confirm our actual weights fall within this range. This uniform initialization is carefully chosen to prevent gradient problems at the start of training. Understanding this structure helps when debugging or implementing custom LSTM variants. Let's visualize the weight distributions for each gate to better understand their initialization patterns. Beautiful visualization of the gate weight distributions. Each gate shows a uniform distribution centered around 0, but with slightly different characteristics. The input gate controls what new information enters, the forget gate determines what to discard, the cell gate proposes new content, and the output gate controls what to reveal. All distributions have similar statistics with means very close to 0 and standard deviations around 0.06. This balanced initialization ensures no gate dominates initially, allowing the network to learn which gates should be more active for specific tasks. Now let's analyze gradient flow through the LSTM, which is crucial for understanding why LSTMs work better than vanilla RNNs for long sequences. We're testing gradient flow through a 3-layer LSTM with a sequence length of 15. After computing a simple loss as the sum of all outputs and backpropagating, we check that gradients are healthy, no nans, no infinities. Then we measure gradient norms at each time step. The key metric is the gradient ratio, max over min for LSTMs. This should be relatively small, indicating stable gradient flow. A ratio under 100 is good, under 10 is excellent. Excellent gradient flow characteristics. Our gradient norms range from 0.025 to 0.16, giving us a ratio of just 6.46. This is fantastic. It means gradients are flowing stably through all 15 time steps without significant explosion or vanishing. This is exactly why LSTMs are so effective for long sequences. The gating mechanisms maintain gradient flow much better than simple RNNs. Now let's directly compare gradient flow in LSTMs versus vanilla RNNs to see the improvement. This comparison really drives home the advantage of LSTMs. Look at the log scale plot. The LSTM gradients in blue remain relatively stable across all 30 time steps. The vanilla RNN gradients in red show much more variation and decay. The gradient ratio for LSTM is 12.84 compared to 178 for the RNN. That means the LSTM is about 14 times more stable. This stability is why LSTMs can handle much longer sequences effectively, maintaining useful gradient signals even through many time steps. Here's a helpful reference table of common pitfalls you might encounter when working with LSTMs and their solutions. Shape mismatches often come from incorrect batch-first settings. Memory overflow can happen with too many layers or hidden units. Vanishing gradients might still occur with very long sequences, so gradient clipping helps. Poor convergence usually means initialization issues, but PyTorch's defaults are well-tuned. And remember, Dropout only works between layers, so you need at least 2 layers for it to have any effect. Let me summarize the best practices for working with LSTMs. Start simple with a single layer and add complexity gradually. Always verify tensor shapes with assertions to catch errors early. Use bidirectional LSTMs when you need full sequence context, like in many NLP tasks. Apply dropout only when you have multiple layers for regularization. Use gradient clipping for very long sequences to prevent gradient explosion. Consider projection to reduce parameters in deep networks. And use batch first equals true for easier integration with other PyTorch layers. Following these practices will help you build robust and efficient LSTM models. That concludes our comprehensive tutorial on PyTorch LSTMs. Thank you for joining me on this deep dive into long short-term memory networks. That's all for today. Thank you for learning with me.